All right. Yes. So let us see if I can find the one that I was looking at earlier on. So what we want to touch on this evening now is the ALU. We want to remind ourselves how the ALU set up, because the ALU is an integral part of the microprocessor. The broad topic that we are dealing with it is microprocessor. But there are three main parts of the microprocessor that you need to understand. You need to understand the ALU, which is the arithmetic logic unit. You need to understand the control unit, and you also need to understand the registry. But the most important part of the microprocessor is the ALU. Because the ALU is like the workhorse, or the central part. In other words, it is the central processor of the microprocessor. If you understand what I mean. Everything have to go through the arithmetic logic unit for it to work. All right. And we're discussing a multiplexer last time. Anybody remember what's a multiplexer? Because the ALU, it has a multiplexer in it. It has um a decoder, and it has an arithmetic logic unit. So once you understand those, you know that you get what is known as a slice or a 1-bit ALU. So we're gonna look at a 1-bit ALU right now. To remind ourselves, look at it already the last time. So we're gonna look at it again and remind ourselves. All right, let's see if we can get an image on it. All right, so we're looking at this one. This particular one we're looking at. And this one is a 1-bit ALU. Usually, and we're gonna look at some 8 bits and some 32 bits in a little while. But we're gonna look at this 1-bit first, and we understand exactly what is going on right here. This decoder that you're looking at right here is nothing but a multiplexer. So the multiplexer coming now? No, not a multiplexer. I mean a decoder. This is a decoder. So this is a decoder right here. Right? Right up here is the arithmetic logic unit. And we have been doing arithmetic, not arithmetic, arithmetic unit. Here's the arithmetic unit, which is really a full adder. We have been doing full adder from the associate degree, right? And up here we have a logic circuit, right? Looking at this, all of us can build this from scratch. We can build this from scratch. But this, notice it has A and a B, input A, input B, and a carry in. And we have
sir.
F0 and F1, which is it's really the select lines for the decoder. Can remember that the decoder of select lines, and the output of the decoder depends on the input. It is different from the mux. All is it different from the mux? Anybody remember the basic difference between the decoder and the mux, the multiplexer? How many output does the multiplexer have? One. It have one output.
One.
How many
Yeah.
input and one out?
Right. And the demultiplexer now has one input and many output. All right.
Yeah, it's just the opposite, sir.
Right. The opposite.
Just
And
like the
and
decoder and the encoder.
right, like the decoder and the encoder. All right. So in this case now, we know that for the multiplexer, we know that for the multiplexer, you can use the select line. So if it has two select line for the multiplexer, we can use those two select lines to determine how many input lines we have. But for the decoder, you use the input line to determine how many output lines you're supposed to have. We have two input lines right here for the decoder. So it is just 2 to the 2 or 2 to the n. And this is 2 to the 2. 2 to the 2 is 4. So we have 4 output lines. 1, 2, 3, 4. And that's how the decoder works. So the output depends on the input. The amount of output depends on the amount of input, right? And it is set up like this. And this now is just for 1 bit. So they call it a 1 bit arithmetic logic unit. All right.
So what time the
No,
class they do?
pardon me.
Theater.
8:30. But if we cover what I want to cover before, then we can end it before
No, sir,
8:30.
my sister asked me what time the class are done.
Okay. The sister asking. Okay.
Mm-hmm.
Hi sister. Yeah, man. All right. So this is a 1 bit arithmetic logic unit. So here right here now is a block diagram of the same thing. We have three input A, input B, input C. We have the two select lines for the decoder, and we have carry out, and we have the output. Here they are right now. With, the carry out is connected to the carry in. Right? So this is a carry in, the carry out. This right is a carry in, but this is a carry out, but this carry out is connected to this carry in. You see it? So they call each of these 1 bit a slice or a bit. So how many bits this is now right here?
1, 2, 3, 4, 5, 6, 7, 8. 8 bits.
8. I see it right down here. So 8-bit arithmetic logic unit. Right? And another way, how they set up the arithmetic logic unit, we're gonna look at it right now. We're gonna look at it in both Tinkercad and Tina. But no, not Tinkercad, I mean Deeds and Tina. So we're gonna look at how it's set up in Deeds, and then we're gonna look at the truth table. A matter of fact, I should look at the truth table first. Let me see if I can look at the truth table first for the arithmetic logic unit. So that you understand it better when we are doing the simulation. All right. We can look at this one. We look at this some time ago. All right. So this one right here, we have 4 select pin. Right. We have 4 select pins. It never show you any output, but it does show you the select pins. What can happen with the select pins? And the select pins usually are from no, let me just go back to this a little bit. Where was it? Right here. All right. Yes. So the select pin usually come from the decoder or it come from the multiplexer. But in most cases, it comes from a multiplexer. All right. So let me see if I can. Okay. Right. So these select pins come from a multiplexer. Because you have to use a multiplexer in the ALU. And it is saying that if all zeros, all selection pins are 0, or all the selection lines are 0, then the operation is an addition. So you can add A and B. Take a note of the A and B because for the ALU has 2 input section coming from the registry. And the 2 input section is input section A and input section B. So I tell you that you can add something from A and B. The next one, you can do a subtraction. You can subtract A and B. You can increment A and B. All right? Or you can increment A with 1. You can decrement A by 1. You can increment B by 1, decrement B by 1. You can transfer A, and what I noticed, different ALU will pass A. When I say transfer A, it does pass A. Anything at all that you put in A and the B, or anything at all that you put on the input of the ALU, especially on the A section, it does transfer it out. Once the select pins are like this, I know you put anything at all in the input section of the A, it does transfer back whatever is in the A. It don't transfer the A itself, but it transfer whatever is inside of the A. Right? Inside of the A register. When the selection pin is like this, it's a multiplication. Likewise, like this, it's a complement. This one is a complement already. A complement, B complement. And the complement means that if you put in this, whatever you put in the A section, if you put a 1, if you put a bit of 1, if you put a 1 bit in the ALU, you're gonna get a 0. When the selection pins are like this, when you put something in the B register, you put a 1 or a 0, it will flip it. Alright? Down here now is known as the logical operations. So for the ALU, everything up here so is the arithmetic part, and everything down in this section is the logic part. So this to do with logics, this section of it. Alright? So let us look at another one now. There was this this is not it.
So that's a high-level overview of what makes up using an ALU. So they came up with a
So-
special symbol to wrap it all up, which looks like a big V.
So
another
we're
level of
gonna just look at it. Alright. You see
Wrap it all up, which looks like a big V. Just
alright. Whenever I see this V, it is the symbol for the ALU. It has two sections. This section over here so is the A section, this section is the B section. Right? And I'm gonna explain in a little while after the video. So just watch this last part of the video right here, and then I'll explain.
another level of abstraction. Our 8-bit ALU has two inputs, A and B, each with 8 bits. We also need a way to specify what operation the ALU should perform. For example, addition or subtraction. For that, we use a 4-bit operation code. We'll talk more about this in a later episode, but in brief,
Alright, and the operation code that they're talking about is really the demultiplexer. Because remember that the demultiplexer it is a selection thing. So the demultiplexer depends on the code that you put in, the selection pins that you put in, it will select either the A section or the B section.
1000 might be the command to add, while 1100 is the command for subtract. Basically, the operation code
And that's the select pin. So this will be the select pin. S0, S1, S2, S3. S0, S1, S2, S3. These are the select. These are how you set the select pin. So this is just an example. It might be like this. It might not be like this to do addition. It might be like this. Or it might not be like this to do subtraction.
Sir,
Depends on the design. Huh?
Sir, one quick question. The ALU only has 4 select pins.
Most of them have 4, but some of them will have 5. Because this the one on simulation it has 5. So it depends on the design. You have different type of ALU that might have it's a different design. Because the one that I have on the simulation it has 5, and the codes are a little bit different.
Right, that's what I want to find out then.
Yes.
If it's a 5 pin, what would be the code for addition and subtraction? Or it vary from the 4 pin one? We're
gonna look at it, and I'm gonna let you write them down. I'm gonna do some comparison. You're gonna compare the standard 4 select pin one, and I'm gonna do the one that we have in the D's. The one that we have in the D's, it is 5 select line it has on. So we're gonna look at that. Yeah, 5.
Okay.
Yeah.
code tells the ALU what operation to perform, and the result of that operation on inputs A and B is an 8-bit output. ALUs also output a series of flags, which are 1-bit outputs for particular states and statuses. For example, if we subtract 2 numbers and the result is 0, our 0 testing circuit, the one we made earlier, sets the 0 flag to true. This is useful if we are trying to determine if 2 numbers are equal. If we wanted to test if A was less than B, we can use the ALU to calculate.
We're gonna look at those flags as well on the ALU. 3 flags. It has more flags. A lot of ALU have more flags, but the 3 standard one, the 3 one that they use mainly is these 3.
Calculate A subtract B and look to see if the negative flag was set to true. If it was, we know that A was smaller than B. And finally, there's also a wire attached to the carryout on the adder we built. So if there is an overflow, we'll know about it. This is called the overflow flag. Fancier ALUs will have more flags, but these 3 flags are universal and frequently used. In fact, we'll be using them soon in a future episode. So now you know how your computer does all of its basic mathematical operations digitally with no gears or levers required. We're going to use this ALU when we construct our CPU 2 episodes from now. But before
So
that,
we're gonna stop this one, and we're gonna look at one of them that we did. No, we want to look at this one first, and then we'll go back to the one, to the one in the simulation. I really want to look at this one. I really want to show you this one.
Strawberry,
not this strawberry thing. This strawberry thing is not a part like. All right, so we're gonna look at it. All right.
Hello everyone. In this video, we are going to see the arithmetic logic unit or ALU. So let's start this video. A computer stores information in its registers and RAM and manipulates information through a variety of means. The component that is responsible for our bulk operations, these operations are done by arithmetic logic unit or ALU. As its name implies, the ALU performs both arithmetic and logic operations. In this presentation, we will focus on describing the general functionality of simple ALU. ALU varies between architectures, so this presentation is intended only to deduce the basic concepts of an ALU. So let us start the concept of ALU. A computer's register each stores the same number of bits when we want to make it what is stored in these registers. The register file will be instructed to send the content.
Oh, and next week we're gonna be looking at registers, mainly the RAM and the ROM, and what make them up, and all they related to the ALU, and all the pass information to the ALU.
Of 2 registers to the ALU. In this example, the registers are 8 bits in length. The ALU will perform a calculation on these 2 values and send the result back to the register file to be stored.
All right, remember the A and the B? Let me show you the A and the B again in the truth table that we have right here. Where is it? Where's our truth table again? Is it this one? All right, this is the one that we're using. These are the A and the B right here. See the A and the B? The A register part and the B register part. So once you add something from the A and the B in another way, once the select line stay like this, you can perform addition. You can add number from A and number from B together, you get a result. We're gonna look at that in simulation. Once it stay like this, it's subtraction. Once the select pin stay like this, you can increment 1. You're gonna add on 1. It's like a carry. You understand? This one decrement, take away. All right. This one right here, so B increment and B take away. This one, once the select pin stay like this, for some of the ALU, not all of them, then to transfer anything that is coming from the A section. Remember that you have the A section and the B section. So anything at all that you put in the A section, it will output it. If you put a 1 in the input section of A, it will spit out. It will put out 1. If you put 10, it will spit out 10 in the A. As long as this select pin stay like this. When it stay like this, you can do multiplication. When it is like this, complement, and when it stay like this down here, these are logics. All right. So when the select pins are like this, you can perform logical operations. All right. So let us go back to the video that we were watching. See the A and the B right here? Everybody seeing what's going on now? Everybody get a better understanding? Hello?
Yes, sir.
I don't hear Nashan, I don't hear Swanee at all. Swanee? Ashana? Oh, you hear them?
Yes, sir. May I get it, sir?
Okay.
Sir?
Yeah?
We tell you the ALU what
Sir?
instruction
Yeah? Yes, Swanee?
Sir?
Yes, yes, Swanee? Yes, I'm here, I'm here. Hello? You can type if it giving trouble, you can type in the chat.
Sir, it's not working well now, you know. It's a act up now.
Back up. All right. We're recording it, but it must stay on as much as long as possible.
to perform by sending in a set of control bits that encode a message, or what kind of
All right. Here are the select pins now. So this one is a 3 input select line. So it can perform how many operation this can perform. Three input select line can perform how many operation. Let me see if you remember. 2 to the 3, don't it?
16.
Yes, sir.
No, 2 to the
Yes,
3.
sir.
2 to the 3,
2 times 2, 4.
Yes, sir.
8.
8 operation.
Right.
Oh,
You see them right
8.
here, so? I remember that they work together. The A section and the B section work together.
operation has to perform.
Something like that.
Because the ALU is combinational circuit, it will perform these calculations immediately. Simplifying the bus diagram, we will use a bus notation where we group sets of wires together with number of wires and a
So they
group.
say they use a bus. When they say they use a bus, instead of use a single wire, they use a group of wires. So this is a bus, is a bus, a bus. The one that I built in the simulation is I use a bus. I use some bus and build it.
Of 8 wires, we will simply draw 3 buses like this.
All right, and this is a standard of when you are doing any type of electronic engineers or computer or anything like this when you're doing in the diagram. Instead of drawing all the wires them, suppose this was 100. Could you draw 100 wire right here?
That's all.
So you just put a
Enough
little
time
slash
for
and
that.
put. So you just put a slash and put 100.
Okay. Right.
You understand? So you took this right here. So you put a slash and put 100. So you took this right here. So in
What
this
now?
case now,
What this is called now, sir?
all right.
What?
So this is still the ALU with the registry. So they call it these are
No,
bus we're just
the
discussing.
notation. Matter about the notation. What's the name of using this notation rather than drawing the 8
Um
line? You just use this. What is this
is
notation?
they call it a simplification block diagram, a simplification block diagram, or a simple block diagram.
Simple block diagram. Okay.
Yeah, simplification block diagram.
An ALU can perform whatever arithmetic operation that we know how to implement, such as addition, subtraction, multiplication, decrement and increment operations. Bitwise logical operations such as not, and, or, and other comprise a list of non-arithmetic operations such as value comparison and setting a register's contents to 0. The details of these operations have been already covered in our logic gates video. You can see that video in pop-up I button above. Suppose that we have an ALU that receives 2 control bits. Because there are 2 control bits, we can encode 4 operations for the ALU to perform. I have chosen 2 arithmetic operations and 2 logic operations for an example.
But in this case, it should have choose 3, but it just choose 2 just to explain something. Everybody understand that? Because you have 8 right here, 8 here, and 8 here. It's supposed to be 3 select line, but he's just using 2 of them to show something.
The ALU receives inputs from 2 8 bits registers and sends out 8 bits of information back to the register file. Based on the data from the control bits, the ALU knows which operations have to perform. In this situation, the ALU knows which operations have to perform.
All right. So if both select line are zero, see them right here? If both select lines are zero, what is supposed to do? What the ALU is supposed to do?
Them say.
Add A to B.
So the
You
first two
understand?
numbers, them look on film. Oh, see select line. Right?
You see select line right here.
Oh,
You
all right.
understand?
Yeah,
Eh.
yeah,
And
yeah.
once you how do you set the select line to be zero? Suppose you have switches on it. How do you select it to be zero
In the half position.
in the off position? All right.
Oh,
Once they are turned off, then there are zeros. Then
and
you
the
can
enabler
perform
you would have used.
operation.
Enabler you would have used. Oh,
No, we don't use
no.
enable right on this. We don't have enable on this one.
Oh,
We use select line on this one. Some of them use select line and enable, but in this case, to
I
simplify it, we
just
are just using select line alone,
okay.
right? And a whole lot of ALU, a lot of them, when it is 000 or when it is 00, then you can perform addition. But not all ALU are like this. But most of the time they are like this. Right?
In this situation, the ALU calculates the sum and sends it to the register file. If we change the control bits, we will change the operation is performed because this operation.
All right, you have to look while if you change which bit, Raja? I mean Raja call my name. Which bit, Gio?
Is performed
So that
If you change which bit, listen this now.
because this operation does not need an input from B. Change the operation
All right, make we go back
file.
again.
If we change the control bits, we
So you say if you change what bit?
The control bit.
control it.
All
Control
right,
it.
which unit that they talk about?
I think that would be the Z unit.
The control unit. Remember now, how many things do you have in a microprocessor? What are they? The component, the main components that you have in a microprocessor?
ALU, control,
Yes.
logic, and data part.
Exactly. You understand? So this part that they are talking about, so this select line is really the control unit they come from. You understand? So the control unit control what operation take place in the CPU in the ALU.
will change the operation is performed because this operation does not need an input from B. If we change the control bits, we will change which operation is performed because this operation does not need an input from B.
All right. What operation will take place right here, so now?
Minus
Look at it. Go 0, 1.
0,
Right
1.
though. Right though.
Addition.
Yes. And what they
Increment.
had? Yes, increment. They
Oh,
add
so
one.
A
They add
plus
one.
1 increment.
Yes.
Oh, yeah,
A
yeah,
plus
yeah.
A. So this would come in the output. So supposed to put 5 in the A. What gonna be on the output? I hear somebody say it look while you know.
13.
No, sir.
Oh,
If you put 5 on the input right here, on the A input, what gonna come on the output? 6.
6.
You see it?
oh, as in if you
A
put
plus
by
1.
increment it by,
Yeah.
I think you add it to the
By
8 as in you.
oh no, you had 1 to it. All right. Suppose it is 1 0. What will be on the output? Not A. In other words, suppose you put 1 on this. Suppose you put a binary 1 on this. You're gonna flip it. Right? And
Flip it on.
right. And if you have a 1
And
and 1, this is gonna give you a 0. If you have 1 1 for select line, you're gonna get 0 out.
Yeah.
register. The B register input will be ignored. The ALU will send an incremented value of A register back to same register file. To briefly introduce the logic operations, we will examine one of the simple operations such as the NOT operation. The NOT operation receives only one set of inputs, that is A register value. So again, the ALU will ignore the inputs from B. The NOT operation changes all zeros to ones and all ones to zeros. The not
You understand? And what I call that in computing again? What do you call it? Complement. Remember, it will change. If you select this, all the zeros will turn to 1 and all the ones will turn to 0. See there? Z equal not A. And if I can, this right here, so it's A as it is, don't it? Hmm?
Yes, sir.
Right. If this is not A, what will be this? What will be this right here, so?
1100.
What exactly? Mhm.
operation is applied to each bit in the register individually, otherwise called a bitwise operation. Finally, if we change the control bits, again the ALU will perform a clear operation, which means that we will set the contents of register to 0. For this operation, the ALU ignores both inputs and simply sends out the value 0. Notice that the ALU is sending
Clear.
out 8 zeros because all numbers, even zeros, are encoded with the same number of bits in a computer. In this video, you saw that an ALU series or bitwise of this
All right.
kind of
So
videos.
let us
Thank you.
look at one simulation that we did now. We're gonna look at one simulation that we did. I'm gonna discuss it. All right, look at this one right here, so. All right, let me just zero out everything. All right. So I made this one from scratch.
Well
And
done, sir. Well done.
right, and if you notice that it has a tanks, and if you notice that it has how many select line?
4,
5.
5. Oh, yeah, come
Yeah,
from 0.
5.
Yeah, 0.
You understand? So the truth table that I was showing you for the ALU, um it has 4, but this one has 5. So it will behave a little bit different. Yeah, it will behave a little bit different. For instance, let me see now. If I and by the way, these are the flags over here, right? This is telling us that if we minus 2 number if you minus the 2C number and it count as a 0, then it will tell you that this Z right here denote a 0, that yes, it's supposed to spit out a 0. Here, so the output right, this is the output right here. The output is supposed to spit out a 0. These are registry. We're gonna use these as registry, the A registry and the B registry. Right? These are flags over here, and the flags tell a different thing. If you have an overflow, then this will come on, right? And in the case of what is it? Yeah, it's an overflow. This is 0. And what purpose of this one again? I'm gonna it will come back to me. It will come back to me. But these are the flags. These are those error flags that I'm telling you what is going on and what's supposed to really happen. But these are the outputs. These are the select pins right here, and these are the 2 input registers. All right. So we're gonna run it. By the way, so it's running already. So we see that we can get timing diagram from it, don't it? And we can get
Yes, sir.
VHDL code from it as well. But we're gonna run it. I'm gonna see what's gonna take place now. All right. So if I turn on any of these select bits, I get some 0 age right here. So I didn't put in anything. So it is just spitting out something, and you can put that as for the truth table. If I turn on the carry, you're not gonna get anything. If I press F1, S4, you're not gonna get any. S3 nothing. S2 nothing. S1 you get FF. In other words, everything would be like 1, right? Binary 1. All right. Um, let us put a 1 in this. That's what will take place. So this is a 1 right here, so this work a little bit different. So it's so I can let well we can do the activity. I can find out what this gonna do now. Cause I put a 1 in the A register. So we're gonna find out which one of the select pin will do the transfer. Cause remember that you have what you know the transfer. You can transfer just the A alone, don't it?
Yes, sir.
Remember that part? let me show you which part I'm talking. Yeah. This part right here. The transfer A, see it right here, so anything at all, anything at all that you put in the A register, it will just transfer it over. Right? It depends on what I put on the select pin. So we're gonna look at the select pin again, and you can write down the gray code for the select pin. And when you write down the gray code, it gonna tell you which one of them cost A to transfer. All right, so we're gonna look at it now. All right, so we want the A alone to transfer over here. So we don't want anything else to transfer but just this one alone. Let me see if I remember which one of them. Not this one. Look like it's this one. All right, let me check. Let me check this and see something. If I put a 5 right here, all right, it's still change it. Right, so this look like it. This look like a control pin. This look like the pin, the select pin. That costs only something alone to come from the A. Let me check. Let me check something again. All right, see it? It's showing for the 6 alone. So this is select pin. So the select pin would be S00, S10, S21, S30, S40. So if you write that out, what would you get? You'll get 00100, don't it? Hello?
Yes, sir.
And that
So,
would be for the transfer part. Everybody understand what's going on so far?